Good morning, Rohit.
Sir, today I think this class is in 1 p.m.
Is it changed today?
Sir, Tuesday, no today.
Oh, really? Then what class you had
Uh,
today?
Sir, no class at this time.
Oh, just wait. Actually, yesterday routine has been changed now, so I am like I have lost my ability to think. You are in which semester? Third, no?
Third semester.
Oh, wait. No, I have a class now, 10 to 10:15. I have a class.
Oh, sir, routine is changed.
Yeah. I have a class. Yeah. Because still yesterday I remembered, yeah, I have a class from 1. Oh, okay, just let me switch off the other light. Okay, the power is, just a minute. Actually, yesterday your routine has been changed. No, your means, because the new BSc batch has come, and that is why some changes have been made to the routine. Yeah, actually, I was also, just now. I just realized that we actually had class from 1, but this
Yes.
has been shifted to 10 in the morning, Tuesday. Okay,
Oh,
and next class we have from next class tomorrow we have. Oh, then Thursday morning 9 we have class. Okay, Thursday
sir,
morning.
tomorrow no class.
Tomorrow we have from 10 same time.
Oh,
Tomorrow we have from 10, then Thursday morning 9 we have class. Okay, and Friday no class, and Saturday no class. So earlier we used to have class on Saturday, right?
yes.
Yeah, Saturday. So now on Saturday we don't have class. Friday we don't have class. So Monday Monday we don't have class. Tuesday we have. Wednesday Wednesday we have. Thursday. Thursday I have two classes. Okay, on
Sir,
Thursday,
oh,
yeah, Thursday I have two classes for you. Thursday one's from 9 a.m. and the other one is from 1 p.m.
oh,
Okay. So some changes have been made, and that is it's very difficult. So the routine is being changed all the time. It is really very hectic to follow. Really hectic to follow like this. Anyway, so today now, tomorrow at 10 same time, and Thursday two time we have class. Okay, please join class. Uh, some more have to join. Some more students to join. Because maybe many people are thinking like, oh, we have a class from 1 p.m. But actually it has been changed. Okay, anyway, so yeah. Uh, okay. Okay, so last time we were learning about we have learned about the various statements of this Clausius statement and Kelvin Planck statement. So today we will learn about refrigerator and heat engine. So I am directly. I have written the note half, but the coefficient of performance note is not yet ready. So that note I have to write. Tomorrow I will give you the notes on two notes I have to give you. Now one is about the statements, their equivalence, and coefficient of performance derivation. Okay, so this is we have learned. Okay, okay. So we have four people. Okay, let
Are
me
you having any class at the evening after three after three?
today after three. No, no, after three no class. Who, you or me?
No, sir. Your
No, no, I don't have. So I think three. Our department faculties have class on maximum till three, maybe after three no class. But the problem is that I had a class from 9 a.m. today, and which I knew only just 1 hour before the class. That the routine has been changed. From 9 a.m. I have a class. Then again 9 a.m. I did a class. I got some 5 minutes break and then immediately started a class. Anyway, so let's start. So new routine we have to follow. Okay, I'm going to follow the book directly. Okay, today we are going to learn about this refrigerator and heat pump, and from here on we will also try to calculate this expression, this quantity called coefficient of performance, and the relationship between coefficient of performance and the efficiency of a Carnot cycle. Okay. Okay, so we have all your this Carnot cycle and Carnot engine, so work done in Carnot cycle and efficiency of Carnot engine. So all those notes have been given to you. Also, the video materials have been uploaded for each day's class, right? No, I think one video material I did not upload, so I will upload that soon also. And yeah, so today what we are going to learn is we learn about refrigerators or heat pumps, and this is kind of application of second law of thermodynamics. Okay, so if you remember in first law, no, in Carnot cycle is actually a cyclic process. No, we have a set of isothermal and adiabatics. Okay, and they made a cycle. And what this okay, overall what this second law of thermodynamics tell us, second law of thermodynamics tells us how much heat we can take from a source and what percentage of that heat we can convert to work. And in other words, that is known as the efficiency of a heat engine. Okay, so efficiency is work done divided by heat supplied. Okay, that we have learned in the last class. And also, if you recall the statements of Clausius and Kelvin Planck, so they are equivalent statements in the second law of thermodynamics, and they say that um, it is impossible to take heat from a body at a lower temperature to a body at a higher temperature. Okay, you follow. It is impossible to take heat from a body at a lower temperature to a body at a higher temperature unless work is done by some external agency. Okay, so some external thing must do a work. What work? So that it can take heat from a colder body. Okay, heat from a colder body, try to understand, and then you take that heat to a hotter body. Okay, so on that principle this refrigerator concept is based. Okay, refrigerator, fridge. Okay, in fridge what we have to keep on cooling the colder body. Okay, we have to keep on cooling the colder body. I mean, you have to take out heat from the colder body. You take heat. The more heat you take from a body, the colder it will get. Okay, so it's very simple to understand. And but this heat cannot be taken spontaneously. Okay, or by itself you cannot take the heat. In order to take that heat from a colder body, you need to do work with the help of an external machine or some external agency. Okay, and on that principle, on that basis, the principle of refrigerator is based, and on that concept, the refrigerator principle is based. Okay, okay. In Carnot cycle, generally what we learned, we have a source at a high temperature, we have a sink at a lower temperature. And we used to take, okay, let me go back to Carnot cycle. Let me just give me 1 minute. I explain to you. So Carnot cycle is, a lot of numerical problems are there. We have to, I will give you an assignment, some 4 or 5, okay, 1 or 2 questions we'll discuss, and another 3 or 4 questions I will give you for your assignment. Let me just go back to Carnot cycle. Yeah, so this is the okay. So if you recall the heat engine note which I provided to you, so what was they written there? So it was written there that okay, let me annotate this. Instead of talking, if I just annotate, it will be better for you. So we have a source, we have a sink. So source is maintained at a temperature of T1, capital T1. Okay. Now what you do, you take a amount of heat Q1. Okay. So the working substance, there is a working substance. Okay. Let me represent it by A. Suppose A is nothing but working substance. So there is to be a working substance which will take a quantity of heat, capital Q1, from the source. Source, no, this source, it is already written there. So still let me write it source, because whatever we are going to learn today, refrigerator, that will be just opposite of this. Source, you take a heat, the working substance takes a heat Q1 from the source, does a work equal to W, and leaves a quantity of heat Q2 to a sink. This is called sink. Sink is maintained at low temperature, source is maintained at high temperature. Sink at temperature T2. Okay. So you understood. It is taking a heat Q1 from a source maintained at temperature, will do a work which is equal to W, will leave a heat Q2 to the sink, and the sink is maintained at a temperature T1. So in this case, of course, Q1 is greater than Q2, and T1, T1 is the temperature of the source, is greater than T2. W is nothing but uh, sometimes it is difficult to write, so please don't mind, because I am having to write with computer mouse. Difficult. So work done W is nothing but Q1 minus Q2. This Q1 minus Q2 is the work done. Okay, so that is the principle of heat engine. Okay, so I'm removing this and I am going back to the refrigerator concept, because in order to understand refrigerator, sorry, we have to learn this concept. Yeah. So see, here the source is at temperature T1, sink is T2. Here just the opposite happens. You are taking a heat Q2 from the source, oh sorry, from the sink. Here the flow is opposite. In earlier case the flow was up to down, but here the flow is down to up. You are taking a heat Q2 from a sink which is maintained at temperature T2, and you are leaving a heat Q1 to the source. I mean, you are heating up the source, you are cooling down the sink. You are taking a heat from the sink, means what? You are cooling down the sink, and the work done is W in this case. So Q1 is always greater than Q2. Okay, so don't get this confusion. Q1, the source temp, so the heat associated with the source is always greater than the heat Q2 associated with the sorry, with the sink. So here also Q1 is equal to Q2 plus W. Okay. Okay, so let me read it first, and then it will be very easy for you. Difference between heat pump and refrigerator and heat pump. Okay, difference, this thing is not required. In the course of learning this topic, we will learn about refrigerator. Okay, so difference topic is, that is not our topic. Our topic is to learn only about refrigerator. Okay, and we will learn this one. Define coefficient of performance and calculate its value. And what is the relation between coefficient of performance and efficiency? Okay, these two things. Okay, the other one is mathematical. So let us see how far we can go today. Okay, a Carnot cycle is a reversible. Carnot cycle being reversible can be performed in reverse direction. When all the operations of a Carnot cycle are performed in opposite direction, it will absorb an amount of heat Q2 you see here from the sink or cold body. The sink always maintained at a lower temperature than the source, or the sink is nothing but the cold body. Okay, at a temperature T2. So body is cold, heat taken from the body is Q2, but its temperature is maintained at T2. Okay, and transferred to the hot body or the source an Q1 amount of heat Q1 at a temperature T1. Okay, you understood? Same thing. Sink maintained at temperature T2, you are taking a heat Q2, and you are supplying a heat Q1 to the source, which is maintained at a higher temperature of T1. So you can also write it in your own language without writing what is given here. So you can write in your own simple language too. Therefore, mechanical energy has to be supplied to the engine from outside. This is the engine, and so from now again you recall the statement of second law of thermodynamics. In order to take heat from a body at a colder temperature to heat to a body at higher temperature, you have to get uh, mechanical work done by an external agency. And in this case, in the case of a fridge or refrigerator, the compressor is the external agency. I think all of you have refrigerator in your households. So you will find out if there is a compressor or not. Okay, and that compressor is the main external agency which is actually cooling down the refrigerator. So it's already cold, but again cooling down. Okay, so Q1. So what is the energy relationship? So Q1 is equal to Q2 plus W. So this is also we got in the last class when we were learning about Carnot's cycle. Okay, the Carnot cycle working in reverse direction is shown in figure here. Okay, so you understood Q1 equal to Q2 plus QW, because Q1 is always greater than Q2, because Q1 is the heat associated with the Q1 is the heat which is rejected to the source at temperature T1. So higher temperature is higher heat equal to this q2 heat. Q2 heat is the heat of the sink plus the work done by the compressor. Okay, I hope this equation you have understood. So the Carnot cycle works in reverse direction. Okay, reverse direction means it is not working from top to bottom, but it is working from bottom to top. Top to bottom means take heat from a source and leave it to the sink. In bottom to top means take heat from the sink and leave some of the heat to the source. Okay, so it can perform two functions. Okay, it can further cool down the cold body and it can further heat the hot body. So in a reverse direction, what happens? It can cool the cold body. So the sink temperature is cooled down. Why cooled down? Because we are taking a quantity of heat Q2 from the sink. Okay, and uh, and the hot body is heated up. Okay, hot body means the source itself is heated up. Okay, why? Because we are why co- co- uh, it further cools the cold body. Why? Because we are taking heat from the cold body. If you take heat from the cold body, it will cool down further. And if you supply heat to a hot body, it will heat up further. Okay. I hope this is clear to you. So not so difficult to
Sir, is
conceptually.
this non-spontaneous process?
Huh?
Sir, is this non-spontaneous process? This
Yeah, it is
refrigerator.
non-spontaneous. Yeah, because we are having a compressor, and it is the actually the compressor which is taking the heat from the sink this time. Okay, because recall. So recall say state. Okay, can I write somewhere here? Okay, I can write this. So recall. So in order to recall statement of second law. So we have learned in the last class. Okay, we have learned in the last class the statements of second law. Okay, so you recall that okay, I have not given the notes, but I think it's given in the video. You see the video once, and then I will give the note, of course, with time. By tomorrow, I will give it to you. And give means like I upload to Google Classroom, and yeah, this is following from that. Without compressor, it is impossible to take heat from the sink because compressor is the external agency here. Because we have learned that without external agency, heat cannot be transferred from a body at cold temperature to a body at higher temperature. Okay, like a ball, no cricket. All of you play cricket, I assume. So if you don't throw a ball up, will it go up? So a ball is there on the ground. Will it go up spontaneously? No, you have to throw it. So you are doing an external work, and that is why the ball is going up. But once the ball is there in the topmost position after you throw it, because of gravity, it will come down spontaneously. Because there the potential energy is high and the here potential energy is low. Okay, that is another concept. But in order to send the ball upward, you are having to do an external work. You are having to throw the ball upward. And this is also the same thing. In order to take heat from the cold body, you are having to do a work by the compressor. Okay, so you understood this? This is equivalent to this comes from nothing but the second law of thermodynamics. Okay. Okay, so what is the definition of a refrigerator? So from here we can follow the definition of a refrigerator. When a reversed heat engine is used to further cool the colder system, the arrangement is called refrigerator. Okay. When a reversed heat engine is this is a reversed heat engine actually. Reversed means because it is taking heat from the sink. Okay, and in the forward case we take heat from the source, but in the reverse case we take out heat from the sink. Okay, so is this clear to you or not, the source and the sink and these concepts? Okay, So in the reverse, the heat engine is used to further cool the colder system, which is called a refrigerator, okay, or refrigeration. So that is the purpose of a refrigerator now, because we always want to keep the things cool, okay. But where do we keep our refrigerator? We keep our refrigerator in our room, in our kitchen or somewhere. But our room is a room temperature thing. No, it is at suppose 25 degrees Celsius. But refrigerator can be like no very low temperature. It can be only some degrees Celsius. So is it possible to get only a few degree of Celsius? Is it possible to get only a few degree of Celsius temperature from a body just by placing this in room temperature? Is it possible? No, not possible. For this, you need a mechanism, okay, and that mechanism means you need to keep that body cooling. And refrigerator is the instrument or the arrangement which does this job of keeping the inside of the keeping its inside colder, much colder than the surrounding or the atmosphere. Okay. And that is, yeah, I have a question. Anyone has a question?
Yes,
Okay.
sir. Listen, five
Uh,
ten.
just wrong. What is the question?
Maybe.
Huh? Okay. Anyway, if you have a question, you can type in the chat box because I am not able to hear you properly. You can type in the chat box. Okay. So that is a refrigerator. Then there is another instrument which is called heat pump. So when a reverse heat engine is used to heat a hotter system, it is called a heat pump. So okay, let me remove the annotation. Who is talking? Juice Ram. Meeting. I have muted him. Talking means not talking, but some noise I could hear, so I have muted him. Anyway, no problem. Okay, so what is a refrigerator is used to cool up a colder body. Heat pump is to heat up a hotter body. So this source you have to heat the source means it is already hot, but you are again heating it up. Okay, by supplying heat, and that is called a heat pump. Okay. So yeah, so that was the more or less an introduction to a system, two systems where you are your this arrangement is working in the opposite direction. Opposite direction means it's a reversed process. Okay, so a reversed heat engine. Yeah, it is actually it is called a reversed heat engine. Why reverse? Because we are taking up heat from a colder body and we are heating up a hotter body. Okay, so that's why it's called reverse heat engine. Okay, so in your syllabus we are given refrigerator and coefficient of performance, so we will learn about refrigerator now. Okay, so a refrigerator consists of the following parts. Okay, so a refrigerator, it has a chamber to be cooled. Okay, sink at lower temperature. Okay, we all know that whenever we store our food items inside a refrigerator, so it is a chamber to be cooled, or in other words, it's called it acts as the sink. Okay, sink means it acts as this sink. Okay, that is the chamber. An electric compressor, it works on electric supply and acts as external energy to supply mechanical energy from outside. Compressor is this one. This is the external working agency. This will in fact take out heat from the sink. Okay. Then a radiator which acts as the source at a higher temperature. So here radiator which acts as source at a higher temperature, and it has another part called this thermostat which is used to control the temperature of the chamber. Okay, the thermostat is used to control the temperature of this chamber or the sink. Okay, you see, sink is nothing but the chamber. Okay, okay. So I may be tired. I had another class from 9, so taking 2 classes continuously is a bit difficult. Okay, so the working substance is called generally freon. Okay, so working substance in refrigerator is freon. Vapor absorbs a quantity of heat Q2 from the chamber. Okay, vapor, freon vapor, working substance. It takes a heat Q2 from the chamber. Okay, of the refrigerator. The compressor does an amount of work W, and the sum is Q2 plus W. Okay, the working substance takes a heat from this chamber, and the compressor does a work. Okay, and the total summation of the work is nothing but Q2 plus W. Okay, this is the heat transferred or rejected to the atmosphere source. Okay, with the help of the radiator. Okay, so this quantity of heat is being rejected. This quantity of heat is being rejected by the system to the atmosphere, and the radiator helps in transferring this quantity of heat to the atmosphere. Okay, so Q2 heat is being taken with the help of the working substance, and this compressor does a work. So total quantity is Q2 plus W, which is being taken to the source. Okay, with the help of the radiator. You have understood. This is same from the this figure 7.3. You can see here. During each cycle, the chamber loses an amount of heat Q2, and the temperature goes on falling. Okay, during each cycle of operation, the chamber loses a Q2 amount of heat. And you know, if a body keeps on losing heat, keeps on heat is being rejected from a body or is being taken from a body, it will cool down. Okay, as soon as the desired temperature is reached, according to setting up a thermostat, the thermostat switches off the compressor. Okay, so thermostat is there, which is used to control the temperature. And when you reach some desired temperature, suppose you need 5 degrees, 10 degrees Celsius, in that case, the thermostat switches off the compressor. Okay, otherwise the compressor will keep on working. Okay, and the compressor is the external agency that keeps on working to reduce the temperature of the chamber of the refrigerator. Okay, the inside chamber is thermally insulated, and the insulation cannot be absolutely perfect. Okay, so it's thermally insulated. Why? Because we don't want outside heat to disrupt our refrigeration mechanism. Okay, therefore, as much as possible, so you go and see your refrigerator if it is insulated or not. If it is no more not insulated, then heat means the refrigerator will not be as it is, or there will be no purpose of using a refrigerator at all, because it will get heated because of the atmosphere, no? Because the atmosphere is always at a higher temperature than the refrigerator. Okay, therefore the chamber is well insulated. Insulated means so that there is no heat transfer between the atmosphere and the chamber of the refrigerator. Okay, therefore some heat slowly enters the chamber and the temperature. Okay, okay, so the chamber is thermally insulated. The insulation cannot be absolutely perfect. Okay, there may be some small gaps in the insulation. This is the for which the thermometer is set. Okay, okay, so this is it. Okay, now coefficient of performance. Okay, so that was more or less about what is a refrigerator, what are its different parts, and how it works. Okay, drink some water. Okay, now what is the coefficient of performance? The coefficient of performance is something like this. This is just the opposite of mm, not opposite, a bit different from the Carnot's efficiency. Okay, so what is the definition of coefficient of performance? Let us see. The coefficient of performance of a refrigerator is defined as the ratio of the heat withdrawn from the cold body to the work done. Okay, so coefficient of performance is this quantity. Let me annotate. Okay, some chat is there. Oh, okay. Yeah, yeah, you can get off. No problem. You can, no problem. So, no problem. I am recording this video and it will be uploaded to Google Classroom. No problem with that. You can see it later also. Okay, so what is coefficient of performance? It is, okay, let me annotate. This one. So it is the ratio of amount of heat. How much amount of heat you have taken from the sink at low temperature? Q2 is the amount of heat which you have taken from low temperature. What is the work done? Work done is Q1 minus Q2. So this is the quantity called okay, some problem is there in my middle. I don't know what happened. This is coefficient of performance. Okay, can you just give me 1 minute? Just 1 minute. Okay, please don't mind. Just okay, I'm back. Actually, a monkey has entered a nearby house. That's why, because a lot of monkey problem is there in my area. Anyway, uh, okay, so we are learning about this coefficient of performance. So it is given by this quantity beta, and it's the ratio of how much heat you have taken to how much work has been done. No, because you see the work done is actually W is equal to Q1 minus Q2. Okay, we have already learned this Q1. Okay, I forgot to write the one. It's one. Okay, so this is the definition of coefficient of performance. Okay, assuming that the machine performs the Carnot cycle in the reverse direction, if Q2 is the quantity of heat absorbed from the cold body at temperature T2, and Q1 is the quantity of heat given to hot body at temperature T1. Okay, so that is what we have already learned from the heat engine diagram, heat engine figure, that you are taking a heat Q2 and you are heating up, you are giving a quantity of heat Q1 to the hot body. Okay, so the work done by the machine is nothing but W. The work done is W. Okay, Q1 minus Q2, And you remember the definition of coefficient of performance. It is the ratio of how much amount of heat you have taken, how much amount of heat you have taken from the sink, and how much work has been done. So this is the expression. Okay, beta is Q2 divided by W. Okay, Q2 by Q1 minus Q2 divided by Q1 minus Q2. Okay, and we have learned this expression already when we are learning about Carnot's engine. So this comes from this. Just for recalling, 1 minus T2 divided by T1 is equal to 1 minus Q2. So this note is given to you already. You can also read it from your note. So Q2 by Q1. So this is the efficiency of a Carnot engine expression. Okay. So 1 is a common expression on both sides. You cancel 1. So we have T2 by T1 equal to Q2 by Q1. So what will have Q1 you take here, take to this side. Q1 by T1, okay, equal to Q2 by T2. Okay. So this expression holds good for Carnot's reversible heat engine. So reversible Carnot's engine Q1 by T1 is equal to Q2 by T2. Okay, how this happens? This happens like this. So so the coefficient of performance can also be expressed in terms of temperature. Both it can be expressed both in terms of temperature and in terms of heat. So in terms of heat, it is Q2 divided by Q1 minus Q2. In terms of temperature, it is T2 divided by T1 minus T2. Okay. So coefficient of temperature is given by this expression called beta. Beta is nothing but Q2 divided by Q1 minus Q2, or in terms of temperature, this is T2 divided by T1 minus T2. This expression. Okay. So all are equal to nothing but beta. Okay, beta is Q2 divided by Q1 minus Q2, or beta is equal to Q2 divided by Q1 minus Q2. That is the expression for coefficient of performance. Okay, I hope this is clear to you. Okay, in the next portion, the relationship between coefficient of performance and the efficiency of a heat engine is given. So this is the efficiency, Carnot's efficiency. We have learned already. Again, I am going to annotation. This is the Carnot efficiency. This eta, this symbol is called eta. Eta is equal to 1 minus T2 by T1. Okay, or T2 divided by T1 can be written as 1 minus eta. Okay, from here. Okay, so what is the value of beta? Beta is T2 by T1 minus T2. So beta is T2 divided by T1 minus T2. We have already found here. So this is beta. Okay, and so divide both numerator and denominator by T1. T2 divided by T1 equal to T1 by T1 is 1, and T2 divided by T1. Okay, so T2 by T1 is 1 minus gamma. So 1 minus gamma is in the numerator now. 1 minus T2 by T1, 1 minus T2 by T1 will be nothing but only eta. Okay, not gamma. Did I call it gamma? So it is not gamma, it is called eta. Therefore, beta is equal to 1 minus eta divided by eta. Okay, so if you were asked to find quickly what is the how would you establish the relationship between coefficient of performance? Coefficient of performance is beta, and efficiency of a heat engine. Okay, beta and efficiency of efficiency of a heat engine and beta coefficient of performance. So the relationship is nothing but beta equal to 1 minus eta divided by eta. So if in a numerical problem I give you the coefficient of performance value, then I may ask you to calculate beta value. Okay, or I may give you the beta value, I may ask you to calculate the coefficient of performance value. So this way there may be numerical problems set. Okay, so anyway, I hope you have understood, and but anyway I will give you the note, so you don't have to worry about that. So slowly I will continue to upload the notes for your reference. Okay. Okay, so we have learned about refrigerator. Refrigerator is nothing but a reversible heat engine. It works in the opposite direction of a heat engine. Reversible means works in the opposite direction. So refrigerator has different. It is a mechanism to work. It has different parts. It needs a compressor to get work done. Get work done to take heat from a colder body to heat up a hotter body. Then we have learned about coefficient of performance. You have to know this definition of coefficient of performance. And once you know this, you can also find a relationship between coefficient of performance and the efficiency of a heat engine. Okay. Yeah, I hope that's all for today. And I am stopping the share here. Yeah. Okay, so I think we are done for today. It's all done. Today we are done. Tomorrow at the same time we have class. Okay, tomorrow from 10 a.m. we have class. Okay, and today's class because the routine has been changed yesterday, and that's why we got a class this morning. Okay. Okay, so see you tomorrow morning, and thank you all for being present in the class. So